All right. So yesterday, we spent a lot of time focusing very specifically on linear equations, graphing them, identifying important parts, manipulating the equations to get them into a very unique format called slope-intercept form. And that format was so important because very quickly, as you saw yesterday, we could graph those lines much more efficiently. We didn't have to do a table where we had multiple sets of work over and over and over again. Typically, the most work we had to do was if the equation wasn't in slope-intercept form, in other words, the y wasn't already by itself, we had to move some pieces around, probably add or subtract a term, divide everything, get that y by itself, and we were set. And that was because from slope-intercept form, we could identify two key pieces of a line, and that was the slope and the y-intercept. So we're going to kind of go in reverse today. So instead of focusing so much on getting the equation or taking the equation and getting it on a graph, we're going to take information describing a line. Now it may be visual, it may be verbal, it may be a little, more discrete in what information is being given to us. But we're going to take that information and we're going to try to write the equation itself. And our end goal is, since it was so useful, we're going to try to make sure that our equation ends up in slope-intercept form. And I'll show you what I mean as we get to those examples here. So the first part of our notes is we're going to figure out how, what process do we follow when writing linear equations given a variety of different information. And the first one here is if we're given a graph. So I have a graph off to the side here. Let me zoom that up for those who are checking in remotely, just for a visual representation, if you want to do a rough sketch or what have you. But what we're going to do here is much more visual in terms of picking out our information. So let me zoom out again so you guys can, if you're writing stuff down on lined paper, give you a chance to jot this down. So our ultimate goal is to find those two key pieces, because in order to write an equation in slope-intercept form, you need to know the slope. You also need to know the y-intercept. Once you know those two values, it's just a matter of dropping them in for the m and for the b in slope-intercept form, and you'll have your equation. So it says first identify the slope. Technically, it doesn't really matter which one you find first, so long as you find both of them. I personally usually find the y-intercept first myself, just because it's a very specific point on the y-axis. So if I bring this coordinate plane up again with our line, very quickly, hopefully, we can spot that the y-intercept, so the point where our line crosses the y-axis, is right here at +2. So our y-intercept is +2. Just as there's no calculations, no funny business, just got to spot it. Now, the slope does require a little bit more work because it's not just staring us in the face. And to find slope, typically, if you're dealing with things graphically, it is best to find slope in terms of rise over run. So for that, it really helps if we have a second point identified on our graph. Now, we have several options. I'm going to just pick one that's a little further away just for variety's sake. But I could choose this point, this point, this point, this point, this point. It doesn't matter which, because all of them will simplify down to the same slope, so long as I count carefully. So for our notes today, I'm going to pick the ordered pair 4, -2. And when I go to count these, let's see, mix my colors up a little bit. I'm going to actually start at my y-intercept, and I'm going to first count my rise, which technically is falling here because of how to get to the same level as the other point. So technically my rise, oh, it's not showing up very well. my rise is going to be down a total of 4 units.
So just because it says rise, it doesn't, you don't technically go up.
Correct. So it's rise over run has been the phrasing I've heard since I was in school. And when we hear rise, we always think up, but it's technically describing a vertical direction, so up or down. The only difference is up is going to give you a positive value, down will give you a negative value. And those signs are important because they will always work out in the end so long as you have the right signs there. Now, from that location, I'm then going to travel right 4 units to reach my secondary point. Right is a positive direction, and that would be my run. So off to the left here of my graph, I'm going to go ahead and identify the pieces that I found. So we just found the slope, which is our M. Now technically we found negative 4 over 4, but what does that simplify to?
-1?
-1. Now, yesterday I was really suggestive in the sense that I recommended keeping slopes as fractions. Now, that was especially true anytime we were going to graph something. We're not actually graphing anything today. We're just writing the equations. So personally, if I was doing it and I could simplify it down to just an integer, I would take it all the way down, and in this case to -1 as well. Second thing we found, well, technically the first thing we found was the y-intercept, and that we already labeled was a +2. So all we did was pick out those 2 pieces, simplifying where needed. So when I slide over here and I'm taking a look at my slope-intercept form, how would I write the equation that describes this precise line that we've been dealing with? I'll do the easy part. Y equals
Would it be 1 + 2?
almost
1x + 2?
closer.
Oh,
That
no.
slope was a -1
Okay.
x + 2. So those signs stick with those values wherever we plug them in at. So this line that we had already graphed for us, we now have the equation for it. So at this point, what would be useful is I could then send this equation to someone else who doesn't have the graph and say, here's the line I'm working with. And they could then, with just enough background knowledge of linear equations, graph the exact same line without even seeing the graph, because trying to describe what it looks like may work some of the time, but the equation will work all of the time. So, not too bad, so long as you can be careful, identify your pieces, count your slope out. I would say if anything would go wrong here, it would probably be a sign issue. Accidentally forgetting a negative, if you went down or went to the left in your rise over run. Second scenario, writing a linear equation given a slope and the y-intercept. This is actually probably the easiest case because it already gave us the information. So all you have to really do is take that slope and the y-intercept, identifying which is which, and make sure to slide them into the right spots. So the slope, for example, is always going to be our M, and the y-intercept will always be our B. So running through that slope-intercept form yet again, this time we'll have y equals -13x - 1. Now, some things I should have pointed out in the last one, don't be alarmed. A lot of times students are really tempted to fill something in for the y or to fill something in for the x, because that's usually our goal, is to figure out what those values are. Those are placeholders. Those are placeholders allowing us to describe how all the ordered pairs in our line relate to one another. And that's what actually creates that very distinct line. I think, not to call you out too much there, Marissa, don't be embarrassed, but Marissa asked yesterday, you know, does the y, I think it was Marissa asked, does the y go into the y-intercept, or the y-intercept go into the y? And I would agree that that's where it gets a bit weird, because we're putting the y-intercept for the b when we actually have a y variable. So although they sound very similar, it sounds like they should be the same thing. They're representing entirely different pieces of information. So you wouldn't be the first if you accidentally tried to plug values into the x and y. I'm just warning you now that those pieces typically remain as variables. All right, the third case here, oh, please don't freeze on me, screen. There we go. Is going to be what happens when those two special cases we kind of alluded to the other day, I think it was 2 days ago. How do we write those equations? Well, it depends on what information you're given. And from that, then you need to just remember how those are particularly formatted. So I'm going to start with horizontal lines. And 2 days ago, when we were graphing using those annoying tables, I said, well, hold on, there is some special cases that are a little bit faster, so long as you remember what they look like. And for horizontal lines, I told you guys yesterday, or 2 days ago, you can tell that you have an equation for a horizontal line when it's y equals some number. There's no x, there's no other extra pieces, it's just y equals a value. What I didn't tell you was that all horizontal lines have a slope of 0. If you wanted to kind of think about it in terms of rise over run, when I go to rise, I can't, because to get to any other point, I'm going to have to stay at the same level. So my rise would be 0 every time over any other value. 0 divided by anything will always turn out to be 0. So all horizontal lines have a slope of 0. So simply, if I came up to you then and said, hey, I have this line, it has a slope of 0, and it goes through this ordered pair. Very quickly, you would already know that, it's a horizontal line. I can figure out exactly where it goes through from there. So for our purposes, we're given this information visually. Clearly, it's a horizontal line, so we know it has to be y equals some number. What would that number be in this situation, do you think?
0.
Not quite. Oh shoot, Dustin here said -3. So 0 represents its slope. -3 is what that y equals. So if you actually think about it, if you consider any ordered pair along this line, you'd have 0, -3, 1, -3, 2, -3, 3, -3, so on and so forth. Same in the negative direction, -1, -3, -3, -3. In fact, every y coordinate would be -3, and that is something that's very unique to these horizontal lines. The y will always be the same value, and then it kind of makes sense then that the equation would tie directly into that. Now, partnered with that 2 days ago, I also talked about vertical lines, which work the same way. They just go the opposite direction, and they use the opposite variable when writing their equations. So instead of y equaling some number, x equals some number. But again, one thing I left out was that the slope of all vertical lines is undefined. In fact, it is the only type of line that technically has no slope whatsoever. And the reason for that is if you were thinking in terms of rise over run, let's say I started here and I counted up to rise 1, 2, 3, 4, or however far. I have 4 over, well, my run, I wouldn't go left or right, would be 0. Some of you may know, though, from the past that do we like zeros in denominators of fractions? No. In fact, if you grab a calculator, any calculator right now, and did any value, say 4, divided by 0, it would say error, or math error, or divide by 0 error, because in the math world, you cannot divide by 0. Mathematically doesn't work. So that is why vertical lines have an undefined slope. Some people will say no slope. I have started to not say no slope because in the past, I've had students when I said, okay, horizontal lines have a slope of 0, vertical lines have no slope. A lot of my students would think, oh, 0 means no slope. No, 0 is a slope. It's 0. No slope is no slope. You can't describe it with any kind of value. Now, this one also has been given to us visually. What would be the equation for this one? X equals what?
3.
3. Perfect. Wow, that was unexpected. There we go. Sometimes my little drawing tool here likes to make random shapes. So the special cases, I mentioned this the other day, are probably some of the easiest ones to graph. They're also some of the easiest ones to write. But if you look at them, they are extremely similar in how they appear. Maybe not visually on the graph, but algebraically through the equation, it's really just the difference between y equals or x equals. So what I would suggest is maybe have these notes nearby today, because on the assignment, there will be some special cases thrown in there, and they may only, allude to themselves as much as saying what their slope is. So just a clue there for today's assignment. So far, ideally, in one way or another, either verbally or visually, we've been given all the information we needed to write our equations. Unfortunately, that doesn't always happen. Sometimes we're only given one of the two pieces, perhaps the slope. Without the y-intercept, we have a little bit more work to do, which is where this secondary formula comes into play. So as I was kind of alluding to, if you don't have both the slope and the y-intercept, or can't at least figure them out quickly, you have a little bit of work to do. So here comes the point slope form. This is a new form for which all you need to know in order to use it is any point on the line, not just the special y-intercept, any point, which will give you a set of coordinates, x1, y1, and you need to know the slope. Now, at this point, I usually make the joke that mathematicians aren't the most creative, and you may have noticed already that the names of these forms in this unit so far have really directly hinted at what information it gives you or what you need to know. So slope-intercept form, you need to know the slope, you need to know the y-intercept. Point-slope form, you need to know any old point, and you still need to know the slope. But so long as you have that information, we can navigate through this new form, point-slope form, and make some adjustments and still end up at that slope-intercept form that we really prefer our equations to be.
So that's how you.
Sorry. Terrell, I saw you jumped in. I wanted to make sure I checked you off my attendance list for today. Thank you for joining us.
Not a problem.
All right. So this is the format. This is going to be something that you're going to see a lot of, and this would be something that I would have available come test time. I don't expect you to memorize it. You may accidentally memorize it from using it a whole bunch, but it's not a requirement. So it kind of sets us up for this scenario here. So we're being asked to write a linear equation. Notice that it is asking for our final result to be in slope-intercept form of a line with a slope of 2/3, which passes through the point -6, 4. Now, I highlighted those two words very particularly because I see the word point, I see the word slope. I'm already starting to think point slope form. But before I even jump into that, I'm a big fan of labeling my pieces before I try to use them. I want to know where they're going, and I want to make sure I don't accidentally mix and match them. So the slope is always denoted by M. And our point, like I said earlier, gives us both an X coordinate and a Y coordinate. That's going to be my X1 and my Y1. Kind of similar to yesterday when we were using the slope formula to calculate the slope. Now from there, I'm going to remind myself that point slope form is Y minus Y1 equals M times X minus X1. And I'm also going to go ahead, just to keep my eyes straight, put my little guideline in there so my equal sign doesn't accidentally jump about. Now, overcome temptation just to fill every variable. The only things we have labeled are M, X1, Y1. So I see M, X1, Y1. I do not want to touch the X. X will stay X. Y will stay Y. Some other things that need to also stay there unless we otherwise adjust them after we fill in our values. These subtraction signs always start there by default. Same with the parentheses. We'll address those in a minute, but they have to be there every time. So as I go through and start pulling out these pieces that I have values for, let's see what happens. So I'm going to have Y minus Y1, which is 4, equals 2/3, which is my slope M, and then parentheses X minus, and here's where it gets fuzzy for a minute, a -6. Now, sometimes I wrap those in parentheses. I don't always do that though when there's another set of parentheses right next to it. Sometimes it almost becomes hard to look at. In this situation, I don't fret too much because I strongly recommend, and some people grumble a little bit because you have to write most of this all over again, but take the extra step, go through and adjust any double negatives you come across, adjusting them to addition or positives. So I'm going to rewrite this same statement yet again. I'm going to zoom in here now to Y minus 4 equals 2/3. And then in parentheses, I'm now going to have X plus 6. Again, nothing's really changed other than that minus a negative, but that's going to at least help me avoid any weird accidental sign flips that trip me up later. Now, here's the good news so far. I'll probably actually, I'm going to run out of space here very quickly. So I'm going to do a quick maneuver here. So when we make our next adjustment, I'll write it up here in just a second. But the good news so far is we have technically written the equation for the line that's been described to us. This is, in fact, the exact equation for a line that has a slope of 2/3 and goes to the point -6,4. If I put it into a fancy graphing calculator, it would give me exactly that line. But I haven't followed all the instructions. It does ask for it in slope-intercept form, and slope-intercept form doesn't look like this. First off, we know slope-intercept form, the y needs to be by itself, but even before that, what should be catching our eyes first? Always catch our eyes.
Parentheses.
Parentheses. Fraction, yeah, we may be a little bit hesitant about it, but those parentheses should say, hey, you know what? You need to do something here before you worry about anything else. And that's exactly what we're going to do first. So I'm not going to touch the left-hand side of my equation. It's still going to be y minus 4 equals. So technically, Dustin, you were right. We are going to use the fraction very quickly, but it's because of what the parentheses are telling us to do, which in this case is to use our distributive property. So 2/3 times x, that's always going to be the easy one because all you really do is write them together, 2/3 x. The second one is going to have you fall back to your comfort level on fractions. Now, if you have a scientific calculator, one that you own, or if you regularly use mine in the classroom, I will gladly show you one-on-one how to input fractions into those calculators. They're wonderful tools, and they're relatively cheap. Now, if it was a piece of equipment that was really expensive and most people didn't have them, I'd say, let's do it by hand every time. I think those calculators are like 10 bucks a piece. But because I don't have a calculator in my hand right now, I'm going to show you the quick mental method that I use when I multiply these fractions. So I'm going to take now the 2/3 times the 6. And what I do in my head is a little two-step adjustment. I'm going to take that positive 6 and multiply it with the numerator. So what's 6 times 2? 12. And then I remind myself that fraction bars are really just division signs in disguise. So I'm going to take that 12 that I got from the 6 times 2, and I'm going to divide it by 3. 12 divided by 3 is 4. That's it. 2/3 times 6 is 4. You could also describe it as, if you ask yourself, what is 2/3 of 6? Well, 4, because 1/3 of 6 is 2. If you have 2 of those thirds, you have 4. Yes, Jay.
So you do 6 times 2, and then.
So 6 times 2, which gives you 12, and then take that 12 and divide it by the 3.
Okay.
Yep, that's where the 4 came from.
Okay.
So good question. Again, with practice, that becomes a much faster process, but without writing it out, it takes a little bit of trust as well. So here we're at over here. We're almost done. The parentheses are out of the way. That looks a bit more favorable, but it's still not in slope-intercept form. And how can I tell?
Because you got 2 4s on there.
Okay, so Jay's saying because of the 2 4s on there, you're dancing around the right idea. Dustin, you're saying slope-intercept form is y equals mx plus b. If I think about y equals mx plus b, a very key piece I could identify is that the y is always by itself. Is the y currently by itself? No. Yep, it's got that -4 we need to adjust. And to get rid of it from this side, I'm going to add 4. But as with any equation, whatever you do on one side, you have to copy it on the other. So on the left, y minus 4, minus 4 plus 4 is 0, which leaves us with our y by itself. Bring down my equal sign. 2/3 x, I didn't touch that anymore, so it's still 2/3 x. And then 4 plus 4 is going to give me a positive 8. So zoom that out there for a moment just to let it sink in. So took a little bit of work. Some things that shouldn't surprise us is in slope-intercept form, right next to the x should be my slope. So I'm still seeing that 2/3 that we were told our slope has to be. But what has seemingly kind of disappeared through that process is I don't see a -6 or a 4 anymore. What I now know differently, excuse me, is the y-intercept is 8. We didn't know that originally, but through a little bit of equation manipulation, we were able to come to that conclusion. Now, don't take my word for it. Let's check real quick. So the ordered pair that we were given was -6, 4. Is that correct? Yep. We know the slope had to be 2/3, but we didn't quite know where that line was going other than that. But the equation we came up with was y equals 2/3 x plus 8. Now, I don't know if you can tell that, but it has a y-intercept at that 8 that we ended up finding, but it goes exactly through the ordered pair that we were given. And if I was to, and I can't trace this particular app, but if you were to count between those 2 points, rise over run, you would go up 4 to the right 6. Well, 4 over 6 simplifies to 2/3. That is the one and only line that exists that has both a slope of 2/3 and goes through that precise point. And we did all that without a graph. Now we can check it graphically, but we use just purely algebra, manipulating an equation to fit our individual needs. Oh, have I frustrated my computer, perhaps? Oh no, I think it froze. Can anybody online hear me still?
Yes.
Well, that's good.
Yeah.
So I haven't lost you. I just need to, aha, I knew it. All right, so slight hiccup there, but we bounced back faster than yesterday, so that's good. So again, I'm not saying you have to graph every equation once you write it. I just wanted to show you that, interestingly enough, we found a very, very specific line. In a world where infinitely many lines exist, we found the one and only one we wanted, with just a little bit of number and equation manipulation. Now, point slope form. It worked really great so long as you had both a point and the slope. Well, naturally, that doesn't always happen. So in comes our friend from yesterday when we introduced the concept of slope, the slope formula, and there's our point slope form again. And the reason why I'm bringing that back is because in this particular example, we're still writing a linear equation in slope-intercept form. But this time, all the information I've been given is that it passes through the points -10, -2, and -15, 5. So I know 2 points that it's passing through. And if I put them on a graph, technically I could count out the slope, but notice I don't have a graph. And even if I did, the graphs I always give you never would fit these coordinates. So even though we may be comfortable with graphing today, I want to make sure that we can still manipulate this even when graphs don't really fit the problem. So the reason why I brought back the slope formula from yesterday, which hopefully if you practice the assignment, there were a couple problems in there where you practiced with the slope formula. The reason why I brought that back is because the slope formula is designed specifically to find the slope given two ordered pairs. And that happens to be exactly what we have. So what's going to happen is we're actually going to have two sets of work here because I have a goal I need to accomplish first before I'm ready to use point slope form. So I'm going to set up my workspace here real quick because you know I'm fancy. So I'm going to kind of cut it here in half. And on the left, I'm going to remind myself that I need to find the slope first. Because without the slope, you can't use point slope form. Oh no, it froze. Oh. All right, recording again. I think I fixed it. All right, so in case you missed that, because I don't know how long it was frozen, I went ahead and split my workspace here into two sections. On the left, I'm going to find the slope first. And as I was saying, the reason why I need to do that is because without the slope, you can't use point slope form. Now, remember, I'm a big fan of labeling information. So over here, with the ordered pairs we've been given, I'm going to go ahead and label that first one, my X1 and my Y1, and the second one will be my X2 and my Y2. Labeling things will help me keep my head on straight. So then over here in my little workspace, I'm not going to write it down a second time because it's literally right here to the left, my slope formula. I am going to fill in each of those individual pieces, the Y2, the Y1, the X2, the X1. I'm going to fill those all in with the values that we now have labeled. Remember though, from yesterday, these subtraction signs in the slope formula have to be there at the beginning. They only change if we bring in more negative values, which looks like it's going to happen. So I'm going to have m equals, put my little fraction bar in here, y2, which is 5, minus y1, which is a -2. On the bottom, I'm going to have x2, which is a -15, minus x1, which is a -10. So all I did was match up the pieces with the values that I had already labeled. Now, as I suggested earlier, oh, got a chat. Of course, my window closed. That's fine, Marissa. You'll have the recording, and I'll post it on Google Classroom as soon as it takes time to upload to YouTube. Yesterday, it took like 45 minutes, I think. So it probably won't be until this afternoon. But yeah, thanks for letting me know, Marissa. All right. So those double negatives, let's clean those up first before we worry too much more about what's going on here. So 5 minus a -2 on top is the same as 5 plus 2. -15, excuse me, minus a -10 is the same as -15 plus 10. And then I can, if I need to grab my calculator, that's fine. Or I can, crunch these numbers real quick. On top, I'm going to have 5 plus 2, which is 7. -15 plus 10 is going to give me a -5. So I find a slope of -7/5. So we now know something that we didn't know previously. Zoom this back out. So we accomplished our first goal. We found the slope. Now we have not only the 2 points we started with, but the slope we now found. So I'm hearing you have a point, you have a slope, you're ready for point slope form. I'm going to sketch that out. So y minus y1 equals m times x minus x1. Put my little guideline in there, keep me on track, hopefully. And thankfully, because I've already been encouraging you quite strongly to label, everything's really already labeled to drop the pieces in. Now, again, the temptation is there. I have something labeled y1. It's right over here. I have something labeled m. We just found it. I have something labeled x1. It's right here. But what happens a lot is anytime there's a second point, my students are very, very tempted to take this x coordinate and put it here. Don't do that. That's not x2. That's just x. We'll leave them be. Same with the y2. Don't put that 5 here. That's just a y. Leave him be as well. The labeling is very specific, so make sure you match accordingly. So as I go through and plug in this information, I'm going to have y minus a -2. I'll come back and clean that up here in just a moment. Equals.
So it's like,
sorry, what?
so it's like the second y and the second x, right?
The second y and the second x in this piece right here.
Yeah.
Yeah, it's those second ones that you'll fill in. The first
Okay.
ones that you see, leave them be. They're going to stay x and y.
Okay.
Good question. So I have y minus y1, which is a -2. M, which is the slope that we found. I'm going to move the negative sign to the top just because a long time ago my teachers told me to do so. So now I just do it. I'm not particularly picky, but it'll help me in just a moment. Parentheses x minus x1, which is a -10. Again, another double negative. I'm going to take an extra line of work here. I'm going to clean that up before I go moving things about. So I'm going to zoom in here real quick. What this will look like is y plus 2 equals -7/5. Then in parentheses, x plus 10. So good news, we have our equation for this line. The bad news, we're not quite to slope-intercept form as requested. What should draw our eyes first?
Parentheses.
Those parentheses. Parentheses should always catch our eye first. So in this case, we're going to do a distribution. So I'm going to leave the y plus 2 alone. I'm going to distribute the -7/5, and that first one's the easy one. You just attach that fraction to that x. The second one requires a little bit of thinking. Again, as a reminder, I'm going to take the 10 times the numerator. So 10 times -7 is -70. What's -70 divided by 5? I'm going to write what I think it is, practicing my mental skills.
15 or 16?
I think it's 14.
Something like that.
I think we would get a -14. So hopefully someone has a calculator nearby to fact check me. But I'm pretty sure if you do that again, 10 times -7 is -70. -70 divided by 5, I believe, is -14. Tiara, is that a head nod for me?
Yeah, I got -14.
Good. So we're on
I
track.
did too.
Yep, no problem. All right. Parentheses are out of the way. What's the only thing left to do?
Put the -2 under the 2 and the -2 under the 14.
Yep, because we're trying to get that y by itself. So I'm subtracting the 2 from both sides. That removes it from the left, leaving me with y by itself equals -7/5 x. And watch those signs carefully. -14 take away 2 will give me a negative 16.
Get ready to go to the lockdown drill just for a few minutes here.
Okay.
I'll shoot out the group and see.
All right. So just a quick summary there. That process, depending on the information that you're given. Oh, yeah, I should turn the screen on, shouldn't I? Whoops. Thanks for looking out, I got it. Look at the past two ones. If you already have a point and the slope, you're good for point slope form. If all you have are 2 points, you need to find your slope first, but then run through that same process. Now, good news, if you get really good at point slope form today, on Monday, the process that we use is going to reuse point slope form a lot. So practice it well today. Monday will be a whole lot easier as a result. Now, there we go. Right there. So those of you at home, if you want to write this all down now, that's fine. It'll also be posted in Google Classroom, a completed copy. What's that? I'll bring it back for the one that you missed. I'll get you. So the last thing we're going to end on today are word problems. And word problems usually throw people off, which is ironic because the question that's typically asked most often in a math classroom is, when am I ever going to use this? Well, then you give those students some word problems to say, this is exactly where you could use this. Well, they don't like that either. So this is, in fact, a situation where being able to manipulate and write linear equations could allow you to solve bigger problems in a real world environment. So what's usually intimidating about word problems is that, we're used to working with the equations, but we're not so used to writing them ourselves. Give us an equation, we can solve, change it, do whatever we need to. But asked to write one, sometimes it's harder to pick out the information we need to write it successfully. So what I've done here is try to give you kind of a mindset, because we're still talking linear equations, and ideally we still want them in slope-intercept form. So boil it all down, I'm pretty much just asking you to find the slope and the y-intercept. So it helps to know, outside of what they mean for just the line, what they mean in terms of the real world. So slope, often in a math class, is referred to as a rate of change. So what that means is how something is changing in relation to something else. So in this particular example, the slope is often the value that is describing how one unit of measurement is changing with respect to another. And it's usually with respect to time or distance. Those are the two, probably the biggest ones over time. So slope is a rate of change. It's measuring how something's changing in relation to something else. It's describing change at its most core concept. The y-intercept, on the other hand, if you think about when we were using it to graph, it really kind of served as our starting point. Once we got that y-intercept on there, it didn't move, it didn't change, it was what it was. So in a word problem, because of the consistency, because of how constant it remains, the y-intercept often remains constant itself. So some sort of measurement, some unit that starts off as one value and doesn't change throughout that process. So again, just to quickly summarize it, slope describes how something's changing. Y-intercept describes something that does not change. Take out those two pieces, identify them as your slope and y-intercept, you can write your equation. So the example we have here, when visiting Baltimore, Maryland, you need to rent a taxi to get from your hotel to the National Aquarium. The taxi company charges a flat fee of $3 for using the taxi and 75 cents per mile. write an equation in slope-intercept form that models this situation. So this is a slightly easier example just to start us off here. But I've been given two values. So we could, at the very least guess which is which, but I want to do more than that. I want to be confident in our guess. We were given $3, we were given 75 cents. Which of those do you think is the slope? 75 cents. Why?
Because it changes per mile, or it's
You're on the right track.
something like that.
So it's not necessarily that the 75 cents itself is changing per mile.
It's the mile. The amount that you're going to pay is going to change per mile by 75 cents.
That was a great way to describe it. So the 75 cents is describing basically how the total is going to change with each additional mile driven. So even though the 75 cents itself, the value doesn't change, it's describing how something else is changing. So I would absolutely agree. 75 cents per mile would be our slope. Well, obviously that must mean the other ones are y-intercept, but I want to defend why that is. Why would the $3 be the y-intercept?
It's a starting point.
Starting point, doesn't use the words flat fee. A flat fee, when you pay something, means that everybody pays it. Whether you're going, a block, everybody's going to pay that $3. Whether you're going across town, you're still going to pay that $3. It's constant for everyone. So that I would actually underline with that flat fee, because that would defend why it's going to be our y-intercept. All right, so we have our pieces identified. The slope, of course, will be our m. The y-intercept will be our b. Now we need to write the equation in slope-intercept form, of course. So y equals what?
Y equals 0.75x plus 3.
0.75x plus 3. And I'm going to go ahead and keep those decimals kind of in there where they were, just so I can remember that we're talking about money as a measurement, because we're actually going to use this equation we just wrote to solve for a particular calculation. So that is our equation. That is describing this taxi company. So used to be back in the day, their meters were tied directly into the car and it tick, 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 measured the miles, calculated it that way. Nowadays, things like Uber or Lyft, they use GPS in the smartphone and they measure that out, and you already know how much it's going to cost you before you even do it. And the way that those apps work is that it uses something like Google Maps to map out the distance, which gives you your miles. It plugs it into their equation, which probably looks kind of like this one, where they probably charge you a flat fee for using their service. And then they add to that, a longer trip is going to be a more expensive cost. So those apps are using these linear equations. So someone out there very clever said, why haven't we been doing this? We have the technology, let's do it. So they did. So we're going to do it old school. We're going to do it like we're the computer. We're just really slow computers. We're going to use our equation to calculate the cost for using the taxi for 18 miles. Now, we've already identified the slope and the y-intercept. So where would this 18 miles go? Not quite.
No, the x.
It would replace the x in our equation. Y, if you think about it, y is representing our total cost, which equals 75 cents per mile. Remember, I think it was last unit, I said the word per suggests or hints at multiplication. So our miles is here at x plus the $3 flat fee. So 18 miles is going to serve as my X. So when I plug it in, I'm going to get Y equals 0.75 times 18 plus the $3. And hopefully someone has a calculator handy because my decimal multiplication is garbage. 0.75 times 18, 13.5 plus the $3 flat fee, which gives me, right off here to the side, the final cost is going to be $16.50. And just like that, again, we would make lousy computers. But because we're the ones that teach the computers how to do this so quickly, we still serve a purpose. Calculating it by hand isn't practical, but with the technology we have nowadays, once you find your equation, computers are really good at being calculators. So, not too bad there.